Welcome to the deep dive. Forget the serene image of our Milky Way just hanging out in space. Today, we're diving into something far more dynamic: the ongoing movements of our galactic disk and the forces behind this cosmic choreography.
Exactly.
Right.
We used to picture the Milky Way as, well, a relatively stable disk just nestled within its dark matter halo. But thanks to the incredible precision of the Gaia mission, that picture has been completely transformed.
hmm
We're now realizing that the relationship between the disk and the halo isn't fixed. It's evolving.
Okay, so it's not just the stars orbiting within the disk. The entire disk itself might be reorienting, like the whole plane.
Precisely. Our mission today is to unpack the key insights into what's causing our galactic disk to move. We'll be looking at recent research, heavily reliant on Gaia data, to understand these forces and what they tell us about the Milky Way's history and its interactions.
Right.
We'll be focusing on two major players: the potential tumbling of the disk, possibly a relic of its formation, and the significant gravitational influence of our large neighbor, the Large Magellanic Cloud, or LMC.
Okay, let's start with this tumbling idea. Even before Gaia, there were hints that the disk wasn't rigidly fixed within a perfectly spherical halo, right? What were some of those early clues?
What was fascinating is that even before Gaia's detailed mapping, simulations suggested the disk and halo weren't in this static embrace.
Hmm.
Think about the galaxy forming. Gas clouds falling in might not have aligned perfectly with the existing disk, giving it a constant series of, gentle pushes.
Okay, kind of messy.
Yeah, and then the LMC's gravitational tug.
Mm.
These factors were expected to cause some level of dynamic movement. Simulations also indicated that the inner visible part of a galaxy could actually become misaligned with its much larger outer dark matter halo.
So imagine that spinning top again. If you keep bumping it from different angles as it spins, the axis of its spin is bound to wobble, right? It sounds like the same idea on a cosmic scale.
That's a very apt analogy, actually. And these initial ideas led to a compelling prediction from simulations that galaxy halos themselves tend to tumble, essentially rotate slowly in the vastness of space.
The whole halo, the dark matter scaffolding.
Yeah, picture the entire scaffolding of dark matter that holds our galaxy together slowly turning.
Okay, here's where it gets really interesting. If this massive dark matter halo is tumbling, how does that affect the relatively smaller disk of stars sitting inside? Is it just taken along for the ride?
Not passively, necessarily. There's a concept called dynamical friction.
Okay.
Imagine the inner disk, made of stars and gas, moving through the sea of dark matter particles in the halo. It experiences a kind of gravitational drag.
Ah, like resistance.
Exactly. This drag, or dynamical friction, was predicted to create a link, a coupling between the angular momentum or spin direction of the inner disk and the tumbling halo, especially in the parts of the galaxy where visible matter dominates.
So this cosmic drag could essentially synchronize the spin of the inner galaxy with the spin of the dark matter halo, almost lock them together.
The prediction was that if this link in spin direction holds, then as the halo tumbles, the plane of our galactic disk where most of the stars reside should also rotate, but relative to the very distant universe.
Relative to distant quasars, maybe.
Exactly. We can use quasars as a fixed reference point. The predicted rate was tiny, though, around 30 microarcseconds per year.
Wow, 30 microarc seconds. That's incredibly subtle. How could scientists ever hope to measure such a minute change?
Well, that's where the brilliance of the Gaia mission comes in. Even before its launch, researchers, I think it was back in 2014, analyzed its expected capabilities.
Wow.
They realized that its unprecedented precision in mapping the positions and motions of billions of stars could potentially detect this incredibly slow reorientation.
So they anticipated this possibility.
Yeah, they anticipated that any residual movement in Gaia's own frame of reference would be negligible compared to this predicted cosmic tumbling.
So Gaia is like this ultra-stable, high-resolution camera that could finally capture evidence of our galaxy's slow cosmic pirouette.
Hmm.
Have we seen that direct evidence of tumbling relative to quasars yet?
Well, the direct measurement of the disk tumbling relative to the quasar reference frame is still an ongoing quest. As Gaia continues its observations, it's a tough measurement.
Right, still working on it.
However, what's truly exciting is that Gaia data has provided compelling evidence for something related but slightly different: that the Milky Way's disk is tilted with respect to a non-spherical dark matter halo.
Ah, okay, so instead of a uniform tumble within a perfect sphere, we're looking at a more complex situation with a lopsided halo. What led to this idea of a tilted halo?
To understand that, we need to look at some peculiar features in the outer reaches of our galaxy. Stellar overdensities.
Overdensities, like clumps of stars.
Yeah, regions in the galactic halo with a higher concentration of stars than average. Two prominent examples, discovered even before the main Gaia beta releases, are the Virgo stellar stream, also known as the Virgo overdensity, and the Hercules Aquila cloud.
Okay, so these are like clumps of stars hanging out far beyond the main disk. What makes them significant for understanding the halo's shape?
The crucial link comes from considering a major event in our galaxy's history, a collision with a smaller galaxy called Gaia Enceladus billions of years ago.
Right. The Gaia Enceladus sausage.
Exactly. Researchers analyzing Gaia data found that the scattered remnants of this merger could only explain the existence and location of those distant stellar overdensities, the Virgo overdensity and the Hercules Aquila cloud, if the Milky Way's dark matter halo isn't a perfect sphere, but is instead tilted or, asymmetrically shaped.
So, if the halo were a perfect uniform sphere, the debris from this galactic smash-up would have spread out more evenly over time. Is that the idea?
Exactly. In a perfectly spherical gravitational field, any initial clumps of debris would tend to dissipate and mix away relatively quickly. The fact that we still see these distinct overdensities suggests that the underlying gravitational structure, the dark matter halo, must be lopsided, allowing these clumps to persist.
Interesting.
In this tilted halo scenario, the Hercules Aquila cloud and the Virgo overdensity aren't just random collections of stars. They appear to be apocentric pileups of the merger debris.
Apocentric pileups that paints a vivid picture, like cosmic traffic jams where the merger remnants get sort of stuck at the farthest points of their orbits.
Precisely. The tilted halo acts like a gravitational trough, guiding the debris from Gaia Enceladus and causing it to accumulate at these specific locations in the outer halo.
Okay.
This gives us a picture of the outer halo, extending roughly 30,000 light years out, being largely defined by the uneven distribution of remnants from this ancient collision, with the Virgo overdensity on one side and the Hercules Aquila cloud on the other.
And Gaia data really strengthen this idea of these features being connected to the Gaia Enceladus merger, right? You said they linked them.
Absolutely. Gaia Data Release 2 provided strong supporting evidence. These two overdensities were found to be located on nearly opposite sides of the sky. They exhibited similar orbital characteristics,
Uh-huh.
and remarkably, the chemical composition of their stars, their metallicity, matched that of stars identified as belonging to the Gaia Enceladus merger. It's like finding matching fingerprints at two distinct crime scenes.
That's a pretty compelling case for a tilted halo influencing the distribution of this ancient galactic wreck. Were there other Gaia findings that pointed in the same direction?
Yes. Another study using Gaia DR2 analyzed the shape of the halo within about 30,000 light years and found evidence that it's triaxial,
Triaxial, meaning.
meaning it has three different axis lengths like a squeezed or stretched sphere rather than a perfectly round one.
Okay, not just tilted, but sort of football-shaped, maybe.
Something like that. And interestingly, the longest axis of this triaxial halo was not aligned with the Milky Way's main axis, but was instead oriented in a way that aligned with the observed positions of the Hercules Aquila cloud and the Virgo overdensity.
Wow. So the very shape of the dark matter halo seems to be dictating where these remnants of a past collision ended up.
Exactly. Furthermore, studies using Gaia data to map the motions of stars in the inner halo, specifically a type of pulsating star called RR Lyrae, revealed that this region is dominated by stars on highly elongated or eccentric orbits.
Eccentric orbits, they swing way out.
Yeah, these stars plunge close to the galactic center and then swing far out into the halo. This kinematic behavior is also consistent with a dynamically active and non-spherical halo.
Okay, so we've moved from a simple picture to one where our galactic disk might be subtly reorienting within a dark matter halo that is likely tilted and actively shaping the distribution of ancient merger debris. That's a huge leap in understanding. But you also mentioned another major influence on our galaxy's dynamics, the Large Magellanic Cloud.
Yes, the LMC. It's a gravitational force to be reckoned with in our local cosmic neighborhood. To appreciate its impact, we need a little background. Hubble observations around 2006 gave us very precise measurements of the LMC's motion across the sky,
Right.
revealing a remarkably high transverse velocity. This sparked a debate. Was the LMC making its very first pass by the Milky Way, or was it on a much longer looping orbit?
A one-time flyby versus a long-term companion that would have drastically different consequences for how it affects our galaxy, wouldn't it?
Precisely. And in 2015, research showed that earlier estimates of the LMC's orbit, which assumed the Milky Way was essentially stationary, were significantly inaccurate.
Ah, they didn't account for our own movement.
Exactly. When you factor in that the Milky Way itself moves in response to the LMC's substantial gravity, the calculated orbital period for the LMC becomes shorter, making the scenario of a first-time infall less likely.
Right.
It's like trying to predict the path of two dancers without realizing they are both influencing each other's steps.
So it's a complex gravitational ballet between two massive galaxies, each constantly influencing the other's trajectory.
Absolutely. That research also indicated that the Milky Way's central region, within about 160,000 light-years, can be displaced noticeably both in its position and its velocity over relatively short cosmic timescales due to this ongoing interaction with the LMC.
Our entire galactic core being shifted by the gravitational pull of its satellite. That's a powerful image.
Indeed. And subsequent simulations delve deeper into the likely consequences of this gravitational interplay. They predicted that as the LMC orbits within the Milky Way's dark matter halo, it should create a kind of trailing wake.
A wake, like a boat.
Yeah, like a boat moving through water in both the stellar and dark matter halos of our galaxy. This wake could manifest as observable overdensities and distinctive patterns in the motions of stars again, precisely the kind of phenomena Gaia is designed to detect.
More things for Gaia to look for.
Exactly.
Yeah.
There were even simulations suggesting that the Milky Way's disk might have already been exhibiting some motion relative to the galaxy's overall center of mass before the LMC even arrived on the scene.
So the Milky Way was already a dynamic system, and then the LMC arrived and really amplified those movements. Given that it's our most massive satellite and has recently made its closest approach, its influence must be profound right now.
You're absolutely right, and recent research has actually managed to quantify this influence by observing the motions of very distant objects in our galaxy's halo.
How'd they do that?
Scientists studied populations of K-giant stars, blue horizontal branch stars, and even distant dwarf galaxies, using data from large-scale surveys like SDSS Segway and Gaia Data Release 2 to map their velocities.
Okay.
These distant objects serve as a kind of fixed reference frame. Because they are so far out, they are less affected by the immediate dance between the Milky Way disk and the LMC.
And what did they discover about the Milky Way disk's movement relative to this distant backdrop of halo objects?
Their key finding is that the Milky Way disk is currently moving at a significant speed, approximately 32 kilometers per second, relative to these tracers located far out in the halo.
Whoa, hold on. 32 kilometers per second.
Yep. 32 plus or minus 4 kilometers per second relative to these tracers at distances ranging from about 130,000 to almost 400,000 light years.
That's astonishingly fast. What's the direction of this motion? Is it towards the LMC?
Well, the direction of this movement is in galactic coordinates L, 56 degrees, B equivalent is 34 degrees. And here's the crucial and somewhat counterintuitive part. This direction points back towards an earlier position of the LMC in its orbit, not towards its current location.
Wait, why? Why this apparent lag in direction? That seems odd.
It's because those distant halo tracers have incredibly long orbital periods. They are so far from the galactic center that they respond much more slowly to the LMC's gravitational pull.
Ah.
So while the Milky Way disk, being more centrally concentrated, reacts relatively quickly to the LMC's recent passage, the distant halo is still responding to where the LMC was some time ago.
Okay, I think I get it. Imagine a boat quickly changing direction. The water immediately around it follows, but the distant ripples continue in the old direction for a while.
That's a great way to put it. It's a brilliant moment, really.
Yeah.
So these seemingly fixed distant stars are actually acting like a cosmic breadcrumb trail,
Yeah.
revealing the Milky Way disk's movement in response to a gravitational tug from a now distant LMC.
That is fascinating.
Exactly. And the significant speed of this reflex motion, along with its direction pointing to the LMC's past, strongly supports the idea of a very massive Large Magellanic Cloud on its first infall, or at least a very close first passage.
So the speed confirms the mass.
The magnitude of the Milky Way's movement aligns with numerical models that suggest the LMC's mass upon infall was greater than 10 to the power of 11 times the mass of our Sun. So yes, very massive.
That's truly colossal, far more mass than what we observe in its visible stars and gas.
Precisely. This implies that the LMC arrives surrounded by a very extensive and massive halo of dark matter. It wasn't just the visible galaxy that fell in.
So what are the major implications of all this dynamic activity? How does this revised understanding change our view of the Milky Way's place in the universe?
Well, first and foremost, it means that any future models attempting to describe the Milky Way's structure and evolution absolutely must incorporate the significant disturbances caused by the LMC's arrival.
We can't ignore it anymore.
Exactly. We can no longer treat our galaxy as an isolated entity evolving in isolation. Secondly, when we observe the outer reaches of our galaxy, the stellar halo, we need to be mindful that the very frame of reference we're using, the Milky Way disk, is itself in motion. That affects how we interpret those halo observations.
Right, our ruler is moving. And it sounds like there's still many unanswered questions stemming from these findings.
Oh, absolutely. This research opens up a wealth of fascinating inquiries. What was the detailed structure of the Milky Way's stellar and dark matter halos before the LMC's infall? What is the precise three-dimensional trajectory of the LMC, and how is its path being influenced by the complex distribution of dark matter in both galaxies? Is the LMC losing significant amounts of its own dark matter due to the Milky Way's tidal forces? And if so, where is that stripped dark matter going?
Yeah, lots to figure out.
And what are the broader implications for the entire local group of galaxies, including the future interaction between the Milky Way and our giant neighbor Andromeda? It's all connected.
So this is a really active frontier in galactic research, and we can anticipate even more revelations as Gaia continues to collect and analyze its treasure trove of data, I assume.
Definitely. Gaia Data Release 3, with its even more precise measurements and a wealth of new information like radial velocities for more stars, is expected to shed significant further light on these fundamental questions. The story is definitely not over.
So to bring our deep dive to a close, the Milky Way's disk is anything but a static entity. It seems to be subtly reorienting, potentially a vestige of its formation and the structure of its dark matter halo.
Right, that internal dynamic.
And on top of that, it's engaged in a significant gravitational dance with the Large Magellanic Cloud, resulting in a measurable reflex motion of the entire disk.
A motion revealed by those distant halo stars acting as a stable reference point.
Exactly, that aha moment. It's truly humbling to realize that our galactic home is in constant motion, responding to the gravitational forces of its neighbors. It makes you wonder, what other seemingly stable cosmic structures out there might be undergoing similar dynamic processes that we are only just beginning to discover?
That's a great thought. It really shifts your perspective on the cosmos, doesn't it? What looks still might be anything but.